Okay, so this is the continuation of section 9.1. So some things to note about probabilities, okay? Probabilities are never negative. Okay? You're never going to have a negative probability because something's going to happen, right? I mean, it may be nothing. If nothing happens, then your probability is 0, right? If it's an impossible event. But it's not possible for it to be a negative probability. Your probabilities are always between 0 and 1 because they're always fractions, right? They're always parts out of a total. 0 being your impossible event, and probability of 1 being a certain event. So we saw the impossible event up here, rolling a pair of fair six-sided dice and getting a sum of 15. Not going to happen. A certain event would be rolling a pair of six-sided fair dice and getting a sum less than 15. We know that's going to happen. So that would be a certain event. So it doesn't get more impossible than impossible, and it doesn't get more certain than certain. Okay? Now, the sum of the probability for every outcome is 1. That means, that's another way of saying that the probability of getting the sample space is 1. Well, yeah, I mean, if you're going to do an experiment, something in the sample space is going to come up. You're not going to roll a fair six-sided die and it land on heads. Not going to happen. Okay. Now, remember this with unions and intersections? You might remember this from such hits as sets back in chapter 2, maybe? The probability of A union B, remember the union, we use the word or, is the probability of A plus the probability of B minus the intersection. So remember with sets, we talked about how the union contains the intersection. It contains that overlap. With probabilities, we have to subtract that off so that we don't count the same stuff twice. If we talk about the stuff in A and the stuff in B, and there is overlap, then that overlap will get counted twice. So it'll get counted with A and then with B. So we have to subtract off that overlap so it doesn't get counted twice. Now, we have some terminology for this overlap. Two events are mutually exclusive if they have no elements in common. Okay? If they have no outcomes in common. Another way of saying nothing in common is to say that the intersection is the empty set. Okay, so mutually exclusive meaning they have nothing in common. So let's look at an example. So let's consider a standard 52 card deck. Let's talk about a deck of cards. A deck of cards is half red cards and half black cards. Maybe I should use a slash. I should use a hand sign. So half red, half black. There are 4 suits. There are clubs, spades. Those are both black cards. And then we have diamonds and hearts. Those are red cards. Each suit has 13 cards. And that's ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. So each of these suits has 13 cards. So 13 times 4 is the standard 52 card deck. Now we say 52 cards because we're not counting the jokers. The jack, queen, and king are what we call face cards. The 2 through 10 we call numbered cards. The ace is not considered a face card or a number card. It doesn't have a face on it, doesn't have a number on it. It's just an ace. So now that we've got all that straight, let's talk about the probability of drawing one card that is a 6. We know that there's a total of 52 cards in the deck. How many 6s are in a deck of cards? Well, there's 4. There's the 6 for each suit. So there's a 6 of clubs, a 6 of spades, a 6 of hearts, and a 6 of diamonds. So there are 4 6s out of 52 cards. Now that does reduce. That reduces to be 1 out of 13. Well, that makes sense, right? Because there's 13 cards per suit, and each suit has 1 6. So that kind of makes sense, right? Why is it as soon as I start recording, my dog gets so thirsty? She has a water dish in the bathroom up here, and yeah, nearby here. And so, yeah, there's a, yeah, that's it. Make sure and hork since the, you know, since I'm recording. There you go. Gonna do some good water yarfing. She's classy. She's a classy, classy girl. So a red card. How many red cards are there? Well, half of the deck is red and half is black. So there are half of 20 or half of 52, which is 26. So we got 26 red cards out of 52. That reduces to be 1/2. Now it's okay if you don't go through this step. If you say, okay, red card, I know half the deck's red. There you go. How about a card that is both red and 6? How many red 6s are there? Well, there's the 6 of diamonds and the 6 of hearts. So there's 2 red 6s out of the 52 cards. Okay. So that reduces to be 1 out of 26. So this is an intersection of red and 6. So if we were to write this as the probability, you know, using set notation, that would be a red and a 6. So the 1 out of 26 means that in half of the deck, there will be 1 red 6. Well, yeah, if you think about it, you take, like, say, the clubs and the diamonds, there'll be 1 red 6. And spades and hearts, 1 red 6. Okay, so pause the video and see if you can go ahead and do the next few. The probability of drawing a club, a face card, you know, and so forth. So pause the video and see what you can do with those. So a club, there's 4 suits, so each suit has 13 cards. So there's 13 clubs out of 52 cards, and that's going to reduce to be 1/4. Okay, that makes sense. There's 4 suits, one of which is the clubs. A face card. The Jack, Queen, and King are your face cards. So there's 3 face cards per suit. There's 4 suits, 3 face cards. So there's 12 total face cards out of 52. So that 12 comes from 3 face cards in each suit and 4 suits. So there's the Jack, Queen, King of clubs, the Jack, Queen, King of spades, Jack, Queen, King diamonds, Jack, Queen, King hearts. This does reduce. So let's see, what does this reduce by? 4 maybe? Yeah, so 3 out of 13. That makes sense, right? Each suit has 13 cards, 3 of which are face cards. Look closely at the next 2. The 2 or heart, and then the 2 of hearts. There's a difference there. A 2 or a heart how many cards are either twos or hearts? This is where, this or right here is where we're going to have to reference this. We're going to have to make use of this guy. So because it says or, the probability of a 2 or a heart, according to our formula, would be the probability of a 2 plus the probability of a heart minus any overlap of 2 and hearts. Now, what is it about this one? Why did I wait till F to use this formula? Because of this word right here, or. That's my signal to use that union. All right, so how many 2s are there in a deck? Well, there's 4, one of each suit. Okay. How many hearts? Well, there's one suit of hearts, so that means there's 13 out of 52. How many cards are both 2 and hearts? Well, there's only one, the 2 of hearts. So why did I just put a plus? That should be a minus. Oops. Minus 1 out of 52. Now right here you may have said, well, the probability of hearts would be 1/4. So why did I write it like this? Well, to get a common denominator. So that'll be 17 minus 1 is 16 out of 52. I did not leave myself enough room for this. I always do that. I never seem to have a good idea of how much I'm going to write. All right, and let's see, that's going to reduce by what, 4? 4 over 13. So that was the probability of the 2 or the heart. I know that was a hot mess in there. Sorry about that. What about the probability of getting the 2 of hearts? Now, in cards, when we say the 2 of hearts, that's just another word for and, or the intersection. So this is the probability of 2 and a heart. And fortunately, this won't take up too much room because we just did that one. 2 and heart, there was just one of those. There's only one card that is both a 2 and a heart. All right, here's another or, a red or a black card. All right, so the probability of red or black. Okay, so that's the probability of red plus the probability of black minus the probability of red and black. So I just want to point out, those key words that's making me use that formula. Now wait a minute here. Red, half the suit, right? Or sorry, half the deck. Black, half the deck. What's the probability of getting a card that is both red and black? Well, it's not possible. It's either one or the other. Those are mutually exclusive. Red and black cards are mutually exclusive. So that means this intersection is empty. So that probability is 0. So that's 0. We don't even have to worry about that. So really all we get is 1/2 plus 1/2 equals 1. I'm going to make this look even worse by grouping that together. Now, what if I told you that you didn't need to use this formula? What if you're just like, oh, a red card or a black card, well, that's just the whole deck. That's going to happen. If you pull a card out of a standard 52 card deck, it's either going to be red or black. That's just how there is. So if you got that without using that formula, fantastic. How about a number card that is even? Well, that could be a 2, 4, 6, 8, or 10. Okay, so that means there's 5 number cards that are even per suit. Okay, so that means 5 times the 4 suits is going to be 20 total even number cards. And that's going to be out of 52. So we get 20 out of 52. That reduces by 4. So we'll get 5 out of 13. Again, makes sense. 5 even number cards out of each 13. So you don't always have to use this, especially when it comes to cards. I could totally believe that you guys can kind of count these in your head. You know, same thing with this one. If you didn't use this formula, that's okay. I just wanted to show you how it was used in a little bit easier setting. All right, let's look at some more examples. A school raffle sells 125 tickets. 10 of those 125 tickets are winners. What's the probability of winning? No trick here. No funny business. Just 10 out of 125, right? So there's 10 winners out of 125. We can reduce that by 5. Okay, so we get 2. What's 125 divided by 5? 25? So that probability is just 2 out of 25. So some of these are going to be super quick and easy. So I don't want you, I did want to do some like that so that you didn't think it was a trap. A cooler has 10 orange Fantas and 4 strawberry Fantas. What's the probability of reaching into this cooler blindly and getting a strawberry Fanta? Well, how many ways are there to get a strawberry Fanta? 4, right? So there's 4 strawberry Fantas. Now be careful, is it 4 out of 10? No, there's 10 orange and 4 strawberry. The bottom number needs to be your total because of a probability. So the 4 is the number of strawberries. The bottom, because it's a probability, is your total number. So how many total number of bottles are in there? 14. And then you can reduce that by, 2? So we get 2/7. So for this one, I gave you the total of 125. All you had to do was take the part out of the total. Here I gave you 2 parts, so you had to know to add those together. Okay, example 8. There are 36 outcomes in the sample space for rolling 2 fair 6-sided dice. We've already established that. What is the probability of not rolling snake eyes? In case you didn't know, snake eyes is the kind of what we call getting 2 ones. So what's the probability of not? So that means what is the probability of rolling anything except 2 ones? How many ways are there to get 2 ones? Well, there's only one way for that to happen. Okay, so there's only one way to get snake eyes. So if we're talking about not getting snake eyes, there's only one way to get snake eyes. How many ways are there to not get snake eyes? What must be the rest of the total? So that means there's 35 ways to not get snake eyes. So that probability is going to be 35 out of 36. All right, let's look at something. The probability of getting snake eyes on a pair of dice is 1 out of 36. We just said the probability of not getting snake eyes is 35 over 36. I'm going somewhere with this. Stay with me. The probability of flipping a coin and landing on heads is 1/2. The probability of tails is 1/2. If you're rolling one die as opposed to 2 dice, the probability of 4 or less, right? The probability of rolling a number that's 4 or less is 4 out of 6. The probability of rolling 4 or greater is 2. Or sorry, no, greater than 4. Why did I put 4 or greater? I came back and changed that one. And I should have put, wait, less than 4. This should be greater than 4. That's why I came back and changed that one. You can kind of see where I erased it. Changed that one and didn't change this one. Glad I caught that. That's okay, we make mistakes. Greater than 4. Okay, so greater than 4, that's just the numbers 5 and 6. So there's 2 outcomes out of the 6, right? Where am I going with this? Well, look at these numbers. 1 out of 36, 35 out of 36. 1 out of 2, 1 out of 2. 4 out of 6, 2 out of 6. These are what's called complementary events. So 2 events whose union is the whole sample space and whose intersection is empty, meaning they have nothing in common, but together they're everything. These are called complementary events. Okay? Nothing in common, but together they make up the whole thing. Now, we use A with a little bar over it to represent the complement of A. So we talked about that with sets. You might remember that when we did sets back in chapter 2. So some things to note, and I did try to color code these here for your viewing pleasure. The union of some event and its complement. Together, they make up everything. They have nothing in common. So this is just like that, that super sexy math way of writing it here. They have nothing in common. Together, they make up everything. The probabilities, because they make up the whole sample space, an event and its complement, because they make up the full sample space, their probabilities together add up to 1. Now, be careful. If 2 events are complementary, then they are always mutually exclusive. They have nothing in common. However, it's possible for 2 events to not have anything in common, but not be complementary. Just because you have nothing in common doesn't mean that together you make up everything. So for an example, I put rolling a number less than 3 and rolling a 6. Those have nothing in common, no events in common, but together they don't make up the entire sample space. Okay, so be careful. Now, we can use, almost done, 9 out of 10. Since the probabilities of an event and its complement add up to 1, we can get this algebraic variation. So all I did was subtract the probability of A from both sides of this to get this formula. Now, this is just the formula that says the probability of a complement or a not is 1 minus the probability of that thing happening. So remember back in chapter 2, we typically use the word not with complements. Okay, yeah, I just said that. So what is the probability of not drawing a queen from a standard 52 card deck? This is the formula you're going to use whenever you see something asking you about a probability with the word not. You're going to want to reference this. All right, so what's the probability of not drawing a queen from a standard 52 card deck? Well, the probability of, so watch how I'm going to write this, not drawing a queen, see how I put that bar over it for the complement, is 1 minus the probability of drawing a queen. What's the probability of getting a queen? Well, there's only 4 of them. There's 1 per suit, so there's 4 out of 52. Be very careful here. Don't you go acting like you smoke crack on the weekends or something and tell me that's going to be like -3 over 52. Probabilities are not negative. You do need a common denominator here for this. So that's 52 over 52. So 52 minus 4 is 48 out of 52, which reduces by 4 and gives me 12 over 13. This is a little bit easier to use this formula because it's easier to say, okay, there's 4 queens, and then take those 4 away from the whole deck. That's what I'm doing here. Than it is to say, ooh, let me count up the number of cards that's not a queen. That's a lot of work. It's easier to just say, okay, I know there's 4 queens, so I'm just going to take those out. Okay, in the home stretch here. Describe an event for the following. Now, answers will vary, okay? If I gave you a probability of 1 and I asked you, tell me an event that has a probability of 1. What's something that's certain? Well, you might want to be very careful with this. You don't want to say, oh, the only thing in life that's certain is death and taxes, you know, or something lame like that. You know, give me something a little bit more like, I don't know, flipping a coin, a fair coin, and it landing on either heads or tails. I'm just going to abbreviate because I'm running out of space. How an event of like 0.999. That's pretty darn close to 1, but not 1. So we want something that, now you don't actually have to come up with something exact. It's not like I'm going to say, oh, well, your event is, you know, has a probability of 0.997. So, wrong, good try. No, give me something that's like pretty close to certain. I don't know, maybe like something like the probability of it raining, or the how about the probability that it is going to be dreary in the winter around Chicago. Yep, that's pretty close to certain. We don't get a whole lot of nice sunny days in the winter time. But, you know, something to that effect. You know, something like rolling, you could say something like rolling a fair 6-sided die and, you know, the numbers being 1 through 5. I don't know. I'm actually going to come back to that and see how much room I have with this, because I know this one, 0.5, that's easy, right? Flipping a fair coin and landing on heads or tails, right? Which makes it sound like, you know, makes it sound a lot like that one, so I'm just going to take out the tails. I didn't mean for it to sound like this one. This one says, you know, flipping a fair coin and getting heads, that has a 0.5. Flipping a fair coin, getting tails, that has 0.5. But if I say getting heads or tails, you know, like getting one or the other, okay, yeah, that's definitely certain. An event that is 0, let's stay with the flipping a coin. So it's flipping a coin and getting a shark. I don't know, I'm just making stuff up at this point. That's not going to happen. I mean, I don't think there's a coin with a shark on it. maybe sharks have their own money and they put their pictures on it or something. I don't know. So for these, now that I know how much room I've got, this one is pretty certain, right? But not absolutely certain. This one's pretty uncertain, but not completely impossible, but pretty darn, pretty darn close. So let's think about something where, this, event, we can say like the, what did I say, dreary weather. In probably like February. It's pretty much going to be dreary in Chicago in February. So what's something that is going to be 0.0001? What's something that's not impossible, but it's pretty unlikely that it's going to happen? So take a second and see if you can think of something. All right, so something extremely unlikely, but not completely impossible. How about getting killed by a cow? We've learned now that that's not impossible. It's more frequent than we thought. So what did you learn in your math video today? I learned that it is apparently easier than I thought to get killed by a cow. I wonder if it's the horns. Are people getting like jabbed by bulls? A bull's considered a cow, right? I guess probably just need to wrap this up and not think about the whole how does a cow kill you thing, because I'm really how does it kill you? Does it step on you? Does it kill you in your sleep? Are people like passing out in a field and the cow's like, hey, get up? Because I'm from Alabama. It happens, right? People pass out in cow fields. Anyway, the probability of a coin landing. I haven't been drinking, I promise. The probability of a coin landing on tails is 1. Explain how this can happen. What? Right? How is it that you flip a coin and the probability of that coin landing on tails is 1? Shouldn't it be 1/2? Well, let's just say that I tell you, okay, here, I've got a coin and the probability that it's going to land on tails is 1. How can this possibly happen? It's not a fair coin. Okay? So this could happen. The coin is not fair. That would mean that it has tails on both sides. So if the tail's on both sides, then the probability of getting tails would be 1, right? Because no matter which side it lands on, you have tails. So I know these kind of questions show up sometimes, so that's why I wanted to address that whole unfair coin, unfair die kind of situation. So, all right, that does end section 9.1. If you guys have any input about how cows are killing people, let me know, because I'm curious. Maybe it's other countries. Maybe I'm thinking too American about this. Okay, anyway, I'm going to keep thinking about that. So, yep, so that's the end of section 9.1.